Okay, and we just arrived to the last but not least lecture in that day. Please welcome Philip Wadler.
Let's make sure that this is on. Yep. Can you hear me? Yes. Right. Thank you for that rousing introduction. Let me do the important thing first. Smile. Okay. So that's my way of saying thank you to you for showing up rather late in the evening for a talk. So are you ready? Yes. To learn about the hilarious subject of computability theory? I told you it was hilarious. You're all laughing already. Good. So let's talk about computability. We think of computers as machines, but computer used to be a name for a person, the woman or man that executes an algorithm, a description of instructions to be executed. And algorithms go back to Euclid's Elements in classical Greece, and eponymously, al-Khwarizmi in 9th century Persia. But it's not until the 20th century that we get formal mathematical descriptions of what an algorithm is. And there were 3 different proposals: Alonzo Church's Lambda Calculus, Kurt Gödel's Recursive Functions, and Alan Turing's Turing Machines, and they were all published within a year of each other. It's like buses. You wait 2,000 years for a proper formal definition of algorithm, and then 3 come along at once. Why did this happen? So at the turn of the 20th century, one of the foremost proponents of formal logic was David Hilbert at the University of Göttingen, and he had a dream. His dream was to put all mathematicians out of work. What he wanted was something, if you gave a formal logical description of a problem in mathematics, he wanted an algorithm that you could use to compute whether that statement was true or false. You wouldn't need mathematicians anymore. This was called the Entscheidungsproblem, because it sounds better in German. Keats famously said, "What is true is beautiful, and beautiful true." And Hilbert's belief that the Entscheidungsproblem was solvable was based on the notion that logic is complete. That is, not only that what is provable is true, but that what is true is provable. Unfortunately for Hilbert, he gave a great talk saying, this is the way we do everything, and the day before, Kurt Gödel had delivered his incompleteness theorem, okay, which meant that, to use a technical phrase, Hilbert was screwed. Sorry, I'm using English words you don't know. So right, there's the Entscheidungsproblem, there's Gödel, right, and here's what Gödel did with his incompleteness theorem. What he worked out was how you could use logic to write down, using what he called Gödel numbers, the following statement. This statement is not provable. Ooh. Okay. Think about that. This statement is not provable. So maybe it is provable, in which case you've proved the statement, this statement is not provable, and so you must have proved something that's false, right? Because it says it's not provable, but you've proved it. Now, these days, right, if you live in the UK or the US, the notion that you might prove something that's false, that's just not a problem. But back then, that was frowned on. The idea that you might prove something that was not true, right? It kind of undermines the value of proof, right? And just to stress how far we've come, right? The place in which this notion that if you could prove something that was not true, that would be bad, that was Nazi Germany. So what's the other alternative, right? The other alternative is that the statement is not provable, and then it's true, and then, of course, you have a true statement that's not provable, which is exactly what incompleteness is. It says there are true things that you could never, ever prove. So just by showing you could write down this statement, he showed that there must be true statements that are not provable. And this is not as bad as having a provable statement that's not true, but it's still really annoying, especially if you're Hilbert. So as soon as Gödel proved this, people began to go, oh, wait a minute, maybe the Entscheidungsproblem is not decidable. Now, as long as they thought that you could solve the Entscheidungsproblem, you didn't really need a formal definition of algorithm. You just write it down and you look at it and go, yep, that's an algorithm. It would be like Justice Stewart's definition of pornography. I know it when I see it. But if you want to show there is no algorithm, then you need a formal definition to say, right, here's the whole class of things and none of them work. So the race was on. Now, the first person to win this race was Alonzo Church, and he defined what's called Lambda Calculus, and then he used it to show that indeed the Entscheidungsproblem is undecidable, and Lambda Calculus is the world's simplest programming language. It only has 3 constructs. There they are. We'll see more about those a bit later. And, right, this is pretty cool, right? Not only is it the world's smallest programming language, but it's the oldest, right? It predates the introduction of the electronic computer, which didn't really come along till about 20 years later. And, these days, all of a sudden, every single programming language is bragging that they have lambda expressions. So, my colleagues and I work in functional programming languages. We've done this for years, and pretty much everybody in industry has contrived to ignore what we do, right? Until recently, when all of a sudden, thanks to the need to program distributed computers, all of a sudden, the ideas of immutability from functional programming have become quite useful. So languages like Java are getting lambda expressions. And you can see here the icon for Java, Duke, looking quite smug that he's got lambda expressions. Well, okay, congratulations, Duke. You have caught up to where Alonzo Church was in the 1930s. So after Church did this, Kurt Gödel, remember him, he was visiting at Princeton, where Church was, and he thought that Church's solution was thorough. Well, his exact words were thoroughly unsatisfactory. So Church challenged him. He said, look, you don't like my definition? You come up with your own definition, and I will show the two are equivalent. And that's exactly what Gödel did. He came up with what's called recursive functions, and the actual paper was written down. Gödel came up with the idea based on some work by Hebrand. Church's student Kleene wrote it down, and indeed, Church and Kleene proved the two ideas were equivalent. And so Church went back to Gödel and he said, look, your idea and my idea, they're the same idea. And Gödel said, oh, my idea is the same as your idea. I must be wrong then. So they were at an impasse, and the impasse was resolved by this man, Alan Turing, who was a very young student at the time. I think he was 23. How many of you were 23 yet? Okay, you can still get there. And he wrote a paper describing what we now call Turing machines. And he did something that neither Church nor Gödel had done. He did philosophy. And he said, let's imagine a computer, by which again he meant a person trying to execute an algorithm, and what would the capacities of that computer be? And he said, well, it could only look at a certain finite number of symbols. And the way he explained this is he said, well, if you're looking at a page, you can't tell the difference between 999, 999, 999, and 999, 999, 999 at a glance. And similar arguments to show that what a Turing machine could do and what a computer, that is a person executing an algorithm, could do are the same thing. And again, Turing proved that what he did was equivalent to what Church and Gödel had done. And indeed, so Turing actually went off to then study with Church. And if you read the paper he wrote proving the Turing equivalent, he begins by referring to Turing machines and, quote, the more elegant lambda expressions. So Turing had a lot of taste. And then he proved them equivalent, and then finally Gödel conceded, okay, maybe the three of us have the right idea. Philosophers often argue about, is mathematics invented or discovered? And what I would like to claim is that if you have three independent ideas about what a computer or an algorithm could be, and then later they're all proved to be equivalent, this shows not that you've invented something, but you've discovered something. Right? Only if you can have independent things turn out to be the same is that evidence that, well, they weren't all just making it up. There was something there to be discovered. So 3 in a row is important, right? It's not just sports fans that are impressed by a hat trick. Now, Gödel was 28 when he undermined the life's work of Hilbert, who was then 68. And Turing was 23 when he resolved the dispute between Church, who was 33, and Gödel, who was by then an ancient 30. So all of you young people in the audience, and you're pretty much all young, which is great, you know what to do. Right? Your job is to keep explaining to your elders when we've got it wrong. Right, so that's the first half of the story. And for the second half of the story, I'm going to explain the related ideas that came on later about propositions as types and how they tied in to the story that I just gave you. And I should remind you of one part of your job here. I am speaking a language that is, for most of you, not your native language. And I'm speaking about ideas, which are, for most of you, new ideas. So maybe I will say something you don't understand. If I do that, there's a simple remedy, which is go like this. And people are always scared to go like this. So if you hear something that you don't understand, what you can do, and you just do this. Okay, but if you're not willing to do this, just turn to the person next to you and whisper in their ear. He's talking about lambda expressions. I don't know what lambda expressions are. Do you know what lambda expressions are? And then maybe the person next to you will say, yeah, of course I know what lambda expressions are, you idiot. But that's very unlikely, right? What the person next to you is going to do is they're going to say, no, I don't know what lambda expressions are either. I'm completely lost. At which place, you know that by doing this, you are helping yourself, you're helping the person next to you, you're helping me to communicate properly, and you're helping the whole rest of the audience. Okay? So I'm going to look around the room, and please nod if you are agreeing to ask a question if you don't understand. Nobody's nodding. No, people are nodding in the middle. Okay, people in the middle are cooperative, and then people at the sides are asleep. But if you don't understand, please ask. And so I should stop here and say, are there any questions from the first part of the talk? Anything you didn't follow? Right? Sometimes questions are of the form, you got that wrong, I want to argue with you. You can save those for the end. But questions of the form, I don't understand, please ask immediately. Check how we're doing for time. Okay. So here's another young guy, Gerhard Gentzen. So he was all of 25 when he completed his PhD thesis. And in his PhD thesis, he introduced two systems of logic. One which is called natural deduction, and the other which is called sequent calculus. And before that, everybody used what was called Hilbert-style rules. So he introduced this at 25. Those two systems that he introduced back in 1935 are the same ones that we use today. Okay. And by the way, he also, the use of upside-down E to mean there exists was already well established. The notion of for all was well established, but the idea of indicating for all with an upside-down A, he also introduced that in this thesis. So a very important piece of notation, and the two most widely used systems for logic to this day were all introduced in this one thesis. Okay, so you've got your goals set out for you, okay? And these are actually the rules we use today. So I just want you to focus on these rules, the ones for and these rules, the ones for implication. I'll show you those in modern notation on the next slide. There they are. That's the notation we use today. You can see this is exactly the same as what's written here, except that Gentzen wrote his letters in German, and I've written mine in English. But other than that, they're exactly the same. So how do we read this? Well, let's start with this rule. If we know A implies B, and we know A, what can we conclude?
B is true.
B is true. Right? Here's B. Does anybody know the fancy Latin name for this rule?
Modus ponens.
Modus ponens. Very good. Some of you are very well versed in logic. And this rule is called implication elimination. This rule is called implication introduction. That's why we've got the E's and the I's. And this says, well, how would I prove A implies B? And he says, well, the way you do it is just assume A. So you can write out a proof in which you use A as if it were true, but you don't know whether it's true or not. And then if assuming A is true, you can prove B, then you may conclude that A implies B. If A were true, then we would be able to prove B. That's what implies means. And, oops, sorry, I've got this backwards. There we go. So, any questions about that? We'll see an example in a moment. And the rules for all of logic that work in a similar way. But I'm just going to show one other one, which is the rule for conjunction. So this rule says so let's look at the elimination rules. It says if you know A and B, what can you conclude from that? Well, you could conclude A. You could also conclude B. And then what would I need to know to prove A and B? Oh, sorry, I'm touching the wrong thing. I can't use computers. What would you need to know to prove A and B? Well, if you've proved A and you've proved B, then you can conclude that you have a proof of A and B. So that's conjunction. And you see the rules come in pairs. Introduction pairs, which have the connective below the black line, and elimination rules, which have the connective above the black line. And of course, what does the black line mean? Well, it says if you've proved all the formulas above the black line, then you've also proved the formula below the black line. So notice that if then at a higher level is already there in proofs. I found that very confusing, right? We're writing the definition of what implies means using this black line, which is a different kind of implies. Okay, but this is all really easy. It just means if you understand logic, then you can understand logic. Fortunately, we do all understand logic. So do people believe that they've sort of understood what I've explained? I'll do an example in a moment. Would you like an example?
Yes.
Yeah, let's do an example. Okay. So here's a proof. This is sort of the simplest one I can think of. Let's prove that B and A implies A and B. What a silly thing to prove, right? Of course A and B implies B and A. How could it be any different? Okay, but it's true, right? So we ought to be able to prove it. If we can't prove it, something is wrong. So let's check and see if we can use our rules to formally prove that that B and A implies A and B. So what do we do here? Well, it says we have to assume B and A. So let's assume B and A. So that's that thing written in brackets there. And it says, okay, well, from that, what can we conclude? Well, by one of the rules, right, we could conclude A. And by the other rule, we could conclude the first thing, B. So now I've got proof of A and a proof of B. So I've proved A and B. And now I can discharge the assumption, which is what writing it in brackets means. And you notice I've written this little superscript Z next to it. And I've written that Z here next to this rule. So it says, this is the rule that discharges the assumption. So here, right, we've said, well, wait, I'm assuming I know B and A. How do you know B and A? What lets you make that assumption? Well, this rule here, where I've removed the assumption, I've discharged the assumption, and now I say, knowing nothing at all, I know that B and A implies A and B, with no assumptions. Okay, is that clear enough to people? Okay, now, we can simplify proofs.
Well, you've swapped the order of A and B.
Yes, it's trivial, but it worked. Do you have a question? Is there something you don't understand?
Yeah, the line above the final implication has got A and B both.
Yes, it needs to do, right? So A and B here is an instance of this rule here, where B has been instantiated to A and B, and A has been instantiated to B and A. Okay? Now, so there's a proof. We can also simplify proofs. So let me show you a slightly bigger proof. So here I've got two assumptions, B and A. Let's not worry about where they came from. Right? Maybe B and A are bigger formulas. Right? I just showed you that you can replace B and A by any formula you like. So maybe B and A are bigger formulas I know are true. So using B and A, I've proved B and A. And then here, I've got the proof that we just did. I really can't use computers. Here I've got the proof that we just did, that B and A implies A and B. So remember the rule of modus ponens. So I've proved B and A, and I've proved that B and A implies A and B. So from those two things, of course, I can conclude A and B. But that's kind of a roundabout proof, right? There should be a more straightforward way of proving it. And we can simplify this proof to give us a more direct proof. So what we're going to do is, remember, here we've assumed B and A twice, right? And then that assumption got discharged by this arrow introduction. And here I've got a proof of B and A. Hey, cool, okay, I don't need to assume B and A. I've got a proof of B and A. So I'll just replace B and A, both places it appears, by this proof, and then I don't need, and then I can just stop when I reach here, and I've proved A and B. So that's what I've done. Right, so I've just copied out this bit of the proof with these two assumptions replaced by copying this bit of the proof. I've got that general rule described here. It says, if you have an implication introduction rule and an implication elimination rule, and one appears above the other, so this will have A implies B as the conclusion, and this will have A as its conclusion. So just in this proof, replace the assumption of A by the proof of A, and then you get this proof here. Now notice why I wrote these ... dots. I'm covering up a lot. In particular, right, that assumption might get used more than once. And indeed, in the example we looked at, it was used twice. So when you copy for the proof, you might copy it many times. You might actually be making the proof bigger. Turns out you might be making it a lot bigger. But we'll be making it simpler. And in particular, we will have eliminated this intermediate formula, A implies B. Similarly, right, what if you have an introduction rule for A and B and then an elimination rule? Okay, well, that one's even simpler to do, right? Because from proofs of A and B, we know A and B, and then from A and B, we conclude A. Oh, wait, there's a simpler way of doing that. Just copy this proof here. Okay? And, oh, right, that's what we've done in this example. So here was the first simplification rule. And notice here now I've got an introduction of an and followed by an elimination of the and. And so we can just simplify that and simplify this one similarly. And now from A and B, we directly get A and B. And notice we've removed these formulas that we weren't assuming and we weren't concluding, like B and A implies A and B, and B and A, right, which would appear here. So the only formulas that appear in the final proof are the conclusion and the hypothesis. And it turns out if we had a bigger conclusion or hypothesis, those might have parts as well. But only parts of your conclusion and hypothesis are what you need. Nothing else. You don't need any other bigger formulas like this one or different formulas like this one. Just parts of what you're assuming and what you're trying to prove. And Gensen characterized that by saying you can do proofs that are not roundabout. And the modern name for this is the sub-formula principle. You can prove things only using sub-formulas. And in fact, you could use this to prove consistency because it turned out that there are very, very few proofs that you could write a false not using parts of it, right? Could I have a proof of false? Well, let's see. Such a proof, if I had one, would always simplify down to one that involves false and its parts and nothing else. How many parts are there of false? Not too many. It's a lot like, what part of no don't you understand? Right? False has no parts. So in this way, this subformula principle also allowed Gensen to show the consistency of his logic, that there was no way of proving false from no assumptions. And that was why one of the reasons he was interested in the subformula property. Okay, so that's logic. That's the subformula property. All set? Any questions? Nod if you kind of followed that. Yeah?
Is Gensen a system applies only to classical logic?
Oh, very, very good question. Does this apply only to classical logic? No, it also works for intuitionistic logic, and in fact, it's the intuitionistic variant that I'm showing you. And that turned out later that it works for lots of logic. So it was Gensen, his key idea that he introduced here, is that the rules come in pairs. Introduction and elimination pairs. Hilbert had nothing like that. And these days, this is the key principle that you use when defining a new logic, or indeed a new programming language, is that the rules come in pairs. You have ways of creating things, introductions, and ways of taking things apart, eliminations. And that was a very good question because it works for a wide variety of logics, including intuitionistic, classical, and so on. Good. Any other good questions? Okay, let's press on for a minute then. So let's get back to Alonzo Church and the Lambda Calculus. Now, he introduced Lambda Calculus originally as an abbreviation for writing down logics. It was actually a kind of macro language, for those of you that know what macros are. And it turned out that untyped Lambda Calculus, using macros, you could write down infinite formulas, and using infinite formulas, you could prove false. So it turned out that his first idea for logic was a bad one. But he wrote in the paper, I think I've got this here. Oh no, I don't have it here. He wrote in the original paper, the system may indeed have applications beyond its use in a logic, which turned out to be correct. And as I said, he worked out that it could be used as a model of computation and used to show that the Entscheidungs problem was undecidable. And that was the untyped Lambda Calculus. For using it as a macro language, he found a better way of doing that, which was to use typed Lambda Calculus. So here are the rules for typed lambda calculus, not written in quite the style he used, but close. So how do we type a lambda expression? So lambda xn, right, this denotes a function. Is there? Yeah. So I'll give you a simple example, right? I'll try to give you a simple example. There we go. Lambda x times x. Thank you. It can stay there. Lambda x times x. That's the way you write down the squaring function. It's the function that takes x as an argument and returns x times x as the result. And for instance, if we then apply that to 3, the way we simplify that is we just take the formal argument x and replace it by the actual argument 3, and you get 3 times 3, and then 3 times 3 would simplify to 9. Okay? How many of you have seen something like that before for lambda calculus? Wow! What a well-educated audience. This is fantastic. Okay, so you're familiar with that idea. So if we want to type things, what would we do? We would say, okay, assume x has type A, and if assuming x has type A, you can show the term n has type B. So in our case, big N would just be x times x. So it's a term that might involve x. And showing that big N has type B, then the whole thing has type A implies B. So if x is a number, then x times x, assuming x is a number, x times x is also a number. So lambda x times x is a function from numbers to numbers. So the type of this would be number to number. Of course, the type of 3 is number. So if we apply a number to number function to a number, we get a number. And here indeed is the number that we get. So, and that's the other half of it, right? If L is a function from A to B, and M is a term of type A, then L applied to M, of course, its type is B. That's the way functions work. And similarly for pairing, if M is a term of type A and N is a term of type B, then Mn is a pair whose first component is of type A and whose second component is of type B. And then if L is an AB pair, first of L would be an A, and second of L would be a B. Is that clear to everybody? You've seen things like that before as well? And here's an example of a program. This is the simplest program I can think of. It's the swapping program. So it's a function that takes a B and A pair and returns an A and B pair. And how does that work? Well, you take an argument Z, that's your B and A pair, and then we'll return a new pair, which consists of the second of Z followed by the first of Z. And here's a proof that that program is well typed. Right? So Z is a B and A pair. So second of Z is an A. And Z is a B and A pair. So first of Z is a B. And therefore second of Z followed by first of Z is an A and B pair. And therefore lambda Z, second of Z, first of Z, is a function that takes a B and A pair and swaps the components and returns an A and B pair. And we have rules for evaluating programs. And right, here's our proof that lambda xn has type A implies B. Sorry, a function from A to B. And here's our, say, a proof that m has type A. And here's our application. So how do you apply the function? Well, you do what I did there. You take your actual argument and you substitute it for the formal in the body. So what we'll do is we'll take m, and everywhere that x appears within n, we'll replace it by m. And here's the rule for pairs, right? If m is a pair, if m has type A and n has type B, mn is an A and B pair, and so first of m and n is an A. And how do you compute the first of m and n? Well, of course, it's just the first component, so it would just be m. Okay? This is, by the way, a call by name definition. You could also do call by value, but let's not worry about complications like that. And so what this shows is a couple of things. First of all, it shows that as you reduce a program, as you evaluate your program, the type doesn't change. Let's have a look, right? So here's a program, right? This is our swapping program. Here's a particular pair. It's a YX pair. And then here's lambda z, second of z, first of z, applied to a YX pair. So what do? We take all the occurrences of z and we replace them by the YX pair. And then we get this, which is still well-typed for the reasons that we just saw. And now we've got second of a YX pair, so we can just replace that by x. And first of a YX pair, so we can just replace that by y. And so we get this. And so we get the answer, right, which is well-typed. And by the way, right, the proof that we did that you could always simplify a program, part of that is showing that the process, you could always simplify a proof. Part of that necessarily showing that the process of simplification must terminate. And the reason it terminates is we're always getting rid of one connective in the types. We're either getting rid of an implies or getting rid of a times of an ampersand in the types. And, and that means that you're always getting rid of one thing, and you can't do that forever. It's a bit tricky to show that, but you can show that. So proof simplification always terminates, and for a similar reason, execution of a type program like this always terminates. Right? So you're all used to thinking, right, the halting problem is unsolvable, which is true. If you want to have the full power of a Turing machine or untyped lambda calculus or recursive functions, you need that power that says it may not terminate. But it turns out if you don't build in recursion, which gives us recursive functions, if you don't build that in, then type programs always terminate. So typed lambda calculus is necessarily less powerful than full recursion, but the halting problem is trivial. Everything always terminates. Which is kind of important. I spent so long thinking, for anything interesting, of course the halting problem is unsolvable. But that's not true. There are really interesting things for which the halting problem is not only solvable, it's trivial. So this is what's great about logic and mathematics, is that they can completely turn your mind around. Right? I mean, the unsolvability of the halting problem, that turns your mind around. And then discovering later, and there's this other really powerful thing where it's always solvable, that turns your mind around again. And so this gives you a proof that typed lambda calculus always terminates, and this proof was actually written down for the first time by Turing. Okay, now you might have noticed that this second thing looks a little bit familiar. So this is actually very easy to see. What I'd like you to all do, the organizers, I hope, have got this sorted out. You should all reach under your seat, and you should find strapped there a pair of rose-colored glasses. So can you do that? Reach under your seat and pull out the rose-colored glasses that are there. The organizers, where's Magdalena? It's not here. Maybe they, there you are, right. You did put the rose-colored glasses under all the seats, didn't you? No. Okay, well, organization isn't always perfect. If you had the rose-colored glasses, right, you could put them on, and you could look at what I've just written down, and since they're rose-colored glasses, you won't see any of the red, you'll just see the blue. And if you look at just the blue in what I've written the second time around, you'll see that, of course, it looks very familiar. Right, so the blue bits of everything I've written is just the same as the logic. And indeed, right, so then we have propositions in logic correspond to types in functional programs. But notice that it goes much further than that. Right? It's not just that the propositions correspond to types, but that the terms are actually corresponding to an encoding of the structure of the proof. So terms are proofs. And then it goes further than that. right? Because what's the interesting thing you can do with proofs in logic? You can simplify them. What is the interesting thing you can do with programs in Lambda Calculus? You can evaluate them. And those are the same thing as well. So the most important thing you can do with programs, which is evaluate them, corresponds to one of the most interesting things you can do with proofs, which is simplify them, which was important for showing the consistency of the logic. Okay, so this is what's called propositions as types. It's sometimes also called the Curry-Howard isomorphism. Here's a drawing by Luca Cardelli, which shows the concepts from types and the concepts from logic are the same thing. Here he's just doing it by changing the shapes. It's called the Curry-Howard homeomorphism rather than isomorphism. It's often called the Curry-Howard isomorphism because in a different form, this correspondence between computation on the one hand and logic on the other was first written down by Haskell Curry, I think in the year I was born. And then later, much later, in the 1970s, William Howard wrote it down in pretty much the form that I just showed you. And then he went on to use it to come up with very interesting generalizations of type systems, which we now call dependently typed systems, and what's sometimes called type theory. So there's a huge branch of logic that came out of this paper of Howard, which, as he said, was first written down in 1969, but it wasn't published until 1980 in a Festschrift for Haskell Curry on his 80th birthday. And notice he didn't quite call it propositions as types, he called it formula as types, but now it's usually called propositions as types, or as I said, Curry-Howard. You can also find the ideas going back to work by intuitionistic logicians. So intuitionistic logic was based on ideas very similar to what I just showed you. So it's sometimes called the DHK correspondence after Breuer, Heiting, and Kolmogorov, who were three intuitionistic logicians, sometimes also named after De Broglie, who came up with similar ideas independently of Howard at about the same time. So this is, by the way, why I use the name now propositions as types rather than using the name Curry-Howard isomorphism, because if you don't mention De Broglie, the Dutch get really mad at you. If you don't mention Breuer and so on, then Bob Harper gets really mad at you, and you really don't want Bob Harper really mad at you. So I call it propositions as types. All the names work. Right? And what we saw, right, is that this is a correspondence that gives us not just propositions as types, but proofs as programs, and normalization of proofs, or simplification of proofs, as evaluation of programs. Now, when I first saw this, I thought, oh, that's kind of cute. I didn't realize I was going to base my whole research career around it. And when I first saw it, I saw it for this weird logic that I didn't understand at the time, called Intuitionistic Logic. And what I didn't understand is that it works for lots of things. So it works for intuitionistic natural deduction. There was something in logic called type schemes. This corresponded, it turned out, to what Milner invented as the polymorphic type system for the ML programming language, which was then inherited by many other programming languages, including Haskell, which I've worked with, and indeed it's got into the generic type system of Java. There's a generalization of this idea called System F, done by the logician Jean-Yves Girard in 1972, and that turned out to correspond to something called the polymorphic lambda calculus, which was designed by John Reynolds in 1974. And it goes on and on. So monologic corresponds to something with something called monads, which some of you who are functional programmers will know about. If you don't know about it, don't worry about it. as I said, I was working with intuitionistic logic, but turns out it works for classical logic, and that the embedding from classical into intuitionistic logic that Gödel devised corresponds pretty much exactly to something called continuation passing style, which again was developed by which was developed by many, many, many computer scientists, including John Reynolds, who wrote a very nice paper on it in 1972. And then there's something else that Jean Girard did called linear logic, which turns out to correspond to a nice type system for expressing communication protocols, something called session types done by Kohei Honda in 1993. And that's really interesting, because Kohei, half of what he did, he stole directly with attribution from linear logic. And then the other half was, well, you need to do inputs and outputs. So he added inputs and outputs on top of one half of linear logic. And then much later, Louis Carras and Frank Fennis, about 25 years later, looked at this and went, oh, wait, that send a message and receive a message that Kohei hacked on to 2 of the 4 connectives of linear logic, the other 2 connectives of linear logic, those actually correspond to send and receive. So this is why I work on session types now, because as you've heard today, concurrency and distribution is a really hard problem, right? What is the right way to do it? Nobody knows. But for me, I think that is, if there is a logic that is about talking about communication patterns, that would be a very good place to start. Maybe we can go there to discover something rather than to invent something. I mean, inventions are well and good. Sometimes you have to invent stuff. But if you can discover it, that's even better. And of course, there are many, many programming languages going back to Lisp, which are all based on these ideas from Lambda Calculus. Indeed, the word lambda in Lisp, right, McCarthy got directly from Church, who he was a student of. McCarthy didn't pay as much attention as he could to Church, who I gather was not the best lecturer. So he got the binding rules for Lambda Calculus and Lisp wrong at first, but Scheme fixed that a few years later. So all of these languages have deep roots in logic. Indeed, as we saw, all of them basically have roots that go back to before the first electronic computers were built. And there's a wide range of languages here. How many people here know one of those languages? Not all of them, but one of them. So most of you have been exposed to one of these. This is great. And how many of you have been exposed to, say, JavaScript? Yeah, about an equal number. Ruby? Java? Right. So you've seen both kinds of languages, right? And these are languages based on ideas that are discovered, not invented. Those other languages are only based on ideas that are invented. And you can tell, can't you? Right. So a lot of this conference has been about, details of things like Gen 2 Linux or what have you. And of course, those can be very interesting. But just as Harold stood up and said, you might want to take your knowledge and use it to be a teacher or a lawyer or a politician, and that would be a useful thing to do. He's absolutely right about that. Here's something else you might want to think about doing with your knowledge. You're all incredibly smart, and you will all do incredibly useful things. I really hope that some of you will not just be doing the next version of Linux. I really hope that some of you will be looking for the deep, reusable ideas, like the ones that Turing came up with, and the ones that Gensen came up with, and the ones that Gödel came up with. That is where you should be setting your sights. That is what you are capable of doing. Don't just get sucked in by the day-to-day details of computing, like not being able to get the right thing to go on the screen. Right? Computers can be incredibly frustrating. The day-to-day stuff can be horrible. But there are deep, beautiful ideas here that people haven't found yet. It's not like physics, where gravitation's already been discovered for 300 years. Right? Computers have only been around for like 75 years. We haven't figured out the equivalent of gravitation yet. One of you can be the person to do that. That's the problem that you should turn your mind to. For the reasons I just said, you can encode proofs as terms in a programming language, and there are many, many proof assistants that are based on that idea as well. So it's not just for writing down programs, but for doing proofs that programs satisfy their specifications. All of these ideas turn out to be very helpful. If you want to learn a bit more about this, there's a paper published in Communications of the ACM in December of 2015. I should be very clear on explaining let's see, I think, this one, monads. I had something to do with that. The classical intuitionistic logic, I did a paper that had something to do with that. Session types, I've had a little bit to do with that. I've had tiny things. So far off the end of these, I've not even talked about that. Right? So I want to make very clear. Everything I've told you about today is work by other people. I'm not claiming credit for it at all. So please make no mistake about that. And if you go to this paper, right, it's not the first or only, or maybe even not the best paper for explaining this, but what it will do is it will give you citations of the literature so you can see where all these ideas came from. Okay, I mentioned that Turing's important contribution was to do some philosophy, so I'm going to conclude by doing a tiny bit of philosophy. Oh, no. First I'm going to say, are there any things people didn't understand that they want to ask about? Okay, save up the questions for the end then. So let me do a little bit of philosophy. Let's say we want to talk to aliens. We've actually done this, right? This is a plaque on the side, on the side of the Voyager spacecraft. And you can see there, it's got a picture of two human beings, a picture of the Voyager beside them, so that, presumably the aliens would find the Voyager, they would recognize that, they'd go, okay, that's how big people are. This bit on the left is, each of those lines is the distance from Earth to a quasar, and each line is marked, you can barely see the marks, but it's marked in binary with the frequency of hydrogen, which is why there's a little schema of hydrogen atom at the top that emits from that quasar. So you can identify the quasars, figure out where the Earth is, look at the alien, at the pictures of the people, go, they look tasty, go there and eat them up. This might or might not happen, right? I think if aliens looked at this, right, they could probably work out the lengths of the lines, they could probably work out binary, but whether they would even recognize the pictures of the people, it really depends, right? If aliens are really, really different from us, they might not even understand what that is. That would just be a bunch of squiggly lines. They don't have a visual system to understand what's going on there. On the other hand, if Star Trek is right, the aliens will look and go, oh, they look just like us. But they don't have pubic hair. Okay, so we've tried to talk to aliens, and some of this is stuff aliens might understand, and some of it's not. So what if you tried to send a computer program to aliens? So there's a movie called Independence Day where they destroy the aliens by sending them a computer virus. And here's the computer virus. I had just started working at Bell Labs when this came out, and I looked at that, and I went, wow, it's written in C. A guy I know down the hall did something that got into a big movie. Okay, it's a strange dialect to see because it only has open curly braces. And, well, maybe it's Java? Well, no, this was back in 1996. That was before Java took over the known universe. So, could this happen? No. Right? I mean, alien computers are not going to understand ASCII, let alone C. Right? If we transmitted a program to them and the aliens just wanted to understand it, would they be able to understand it? Well, I don't know. I mean, I think C might be a bit like people, right? They might, depending, it might be very hard for them to crack. If we sent them a program in Lambda Calculus, I think it would be like these lines. Yes, that would be something that they could definitely work out, right? So you might think, okay, should we call Lambda Calculus the universal programming language? Well, let's think about that for a minute, because actually, in popular culture now, people start talking about multiverses, that there's more than one universe. This is from a play called Constellations, which has the best stage direction ever. It only has one stage direction. Stage direction is a horizontal rule in the text corresponds to a change of universe. And then the director turned this into changes in lighting and so on. But it's a play that takes place in many different universes. And people are used to the idea of many universes. Okay. Let's see. So one reason they talk about many different universes is, well, maybe in some of them the gravitational constant would be a bit different. And that might explain actually why our universe has life in it. Because we're here to see it, so we're in one of the universes that's the right value of gravitation so that planets and life would form. So people actually think about things like, well, maybe gravitation would be different in different universes. What about logic? What about modus ponens? So I don't know about you, but my imagination is not good enough to imagine a universe where the rules of logic do not hold. My imagination just can't do it. So we cannot call Lambda Calculus the universal programming language. It just doesn't work, right? And the reason we can't do it is because calling it universal is too limiting. So, okay, that's my talk. I hope you're motivated to go off and study functional languages, and even better, to go off and create the next deep thing, to find the analog of gravitation for computing. Okay? But the real lesson I want you to take away from all this is that when you have a hard problem to solve, that what you should think to yourself is, this is a problem for Lambda Calculus.
Alright, thank you for the show. And do you have any additional questions?
You talked about linear logic and how it connects to linear types, and now we see that linear types are being introduced in programming languages as lifetimes in Rust, and there are also people working on introducing it to GAC, to Haskell as a Haskell extension. And do you think that linear types are going to be the next big thing in programming, like Lambda expressions are now?
Okay. So I'll rephrase the question. Right. So Lambda Calculus, after a long period of time, has been adopted in industry. And your question is, linear logic has deep roots in logic. Will that become one of the next big things? And I don't know, is the answer. I'm certainly working on it. I think there might be interesting things happen. Rust is a really interesting language which took inspiration from ideas in linear logic, but if you look at most of it, it's kind of invented rather than discovered. There's really interesting work to do, I think, finding the discovered equivalent of what Rust is doing. So if somebody does that, or if somebody manages to do that for communication, which session types may or may not be, I think that will become very powerful. I think it's the right place to look. Whether those things will actually succeed, I'm not going to predict. Alan Kay once said the best way to predict the future is to invent it. So if that's the answer you want to the question, You know what to do.
Any other questions?
Oh, come on. You can do better than this. I'll feel it's a real failure if I don't get more questions. Please, some questions. Everybody is shy.
So you showed that we can look at the formal logic like at type lambda calculus, yes?
Yes.
So does it mean that type lambda calculus is actually weaker than Turing Machines and lambda calculus, yes?
Typed lambda calculus, if you do not build in recursion, is strictly weaker than those. But all existing functional languages like ML or Haskell or any of the other ones I showed include recursion as a primitive operator. So the recursion does not correspond to something in a logic, or if it does, it corresponds to paradox, the ability to prove false. But it's easy to add on top of a typed language, and then it does give you the full power of Turing machines.
But my question is what we can actually show is this class of things that we can actually show is smaller than the class of things that we can compute. Because
Right. The class of proofs in natural deduction is smaller than the class of programs in untyped lambda calculus, even though it's identical to the class of programs in typed lambda calculus. You understood? Good. Thank you.
thank you.
Let's imagine that in the future one very smart person will invited that modus ponens, which is the base for Gensen system, is not true in all the time, in all over the world. And what would happen with functional programming?
Well, you could also say, what if you find a corner of the Earth where 2 plus 2 is 5 rather than 4? Right? And you'll say, well, that can't happen. It's a logical
Math is
contradiction.
based on axioms, so it's possible.
Of course, there are many different logics, as I mentioned. But you might find situations that you want to describe using a different logic, and that happens all the time. I don't think you could find that logic is incorrect. And I expressed that fairly clearly by saying I can't even imagine a different universe where these rules don't hold. So I disagree with your premise that you'd find somewhere where these don't apply. Now, I might be wrong in asserting that. In some sense, it is an article of faith. But I've not encountered any situations, and I don't believe there are any. If we find them, then we could cope with that.
You don't believe it could happen in logic, but it happens in physics. For example...
Yes, that's the difference between physics and logic.
Okay, someone else.
So I heard a thing about there's a thing called Gödel's incomplete theorem.
Yeah.
Which I think it states that a math system is either incomplete or inconsistent. And as far as I know, all mathematicians right now are hoping that the math system that we are currently using is incomplete, because if we can prove that it is incomplete, that means that we have possibility that it's consistent. So everything we do in math, it's true, and well, it's true. But what if the math system we are currently using is inconsistent? What does it mean for Lambda Calculus? Maybe in that case, Lambda Calculus is... maybe in that case, it's not a universal language anymore.
Right, so the question, so this is sort of a variant
So the
of
question
the other
is,
question.
So the question is, what does it mean for Lambda Calculus? Is in the case whether in the case of math system we are currently using is not consistent.
Right, so you referred to Gödel's incompleteness theorem, which of course I referred to in the talk.
Yeah.
And you're referring to a more nuanced statement than I did. I just gave the statement as every sufficiently powerful logic must be incomplete. But in fact, as you point out, the correct statement is must be incomplete or inconsistent. And in fact, it's a consequence of that theorem that you can't do a formal proof of the completeness of a system in the same system. You must always use a more powerful system. So for instance, arithmetic has been proved consistent. But to prove arithmetic consistent, you need to assume ideas about transfinite ordinals, which are much more complicated than the basic principles of arithmetic. So indeed, conceivably, we could sometime find out that some version of logic is inconsistent. Now, that will not happen with the natural deduction I showed you, because I showed you the proof that it is consistent. And that's because it's not a sufficiently powerful system, by the way. If it was powerful enough to express all of arithmetic without assuming primitives, then Gödel's proof comes in, and you can't show it. So in fact, the main systems that we use, Lambda Calculus is based on natural deduction. Polymorphic Lambda Calculus is based on system F. These systems have actually been proved consistent. So the thing you're worrying about won't happen. And of course, if we do ever prove that things are inconsistent, we've got much worse problems than the future of functional programming. If we can prove logic is inconsistent, everything Trump has said is true.
Okay, thank you.
But it's a very interesting and deep question. I'll have to ponder it a bit more. Thank you. Anybody else with an interesting and deep question? It's getting late. People may want to go home and sleep. Or go to the pub and drink.
So thank you again for this interesting lecture.
Thank you.
And tomorrow, the third day of our festival, we start at 10 o'clock in this room.